Today, we'll look at the types of interaction, and this is the second part of principle of conservation of momentum.
Look at this, yeah?
Oh,
What if I use two balls instead?
maybe one ball gets knocked out the other side. Really high. Oh,
How about three balls?
maybe all the balls stick together and go out the other side slowly. Oh,
How about five balls?
very funny.
Let's look at the case when we have two balls colliding into the stack at velocity v. This implies an initial momentum of 2mv and initial kinetic energy of 2 times half mv squared. Why didn't the collision result in one ball leaving the stack at velocity 2v? As far as the principle of conservation of momentum is concerned, we are okay because the final momentum is also 2mv. The final kinetic energy, however, is going to be half m bracket 2v squared, or 4 times half mv squared. This is called a superelastic collision because the kinetic energy increases after the collision. This is an impossible outcome for the Newton's pendulum because how are you going to explain where the additional kinetic energy comes from? The actual outcome, as we saw, was actually two balls leaving at velocity v. This implies a final kinetic energy of 2 times half mv squared, which is exactly the same as the initial total kinetic energy. This is called the elastic collision because the kinetic energy is conserved in the collision. Why wasn't the outcome of the collision 5 balls leaving at velocity 2v over 5? Again, this outcome actually satisfies the principle of conservation of momentum. If we look at the final kinetic energy, however, we realize that the final kinetic energy is going to be 5 times half m bracket 2v over 5 squared, which is going to work out to be 4/5 of half mv squared. This is called an inelastic collision because the kinetic energy decreases after the collision. This particular outcome is actually called the perfectly inelastic collision because it results in a maximum possible loss in kinetic energy. We can tell that by the fact that the outcome is all the balls moving off at the minimum possible speed. Now, why did the Newton's pendulum display elastic collision rather than inelastic collision? Whether a collision is elastic or not depends on the colliding surfaces. Collisions between stiff and rigid surfaces, such as steel balls, is highly elastic. Collisions between deformable surfaces, such as plasticine balls, are highly inelastic. So to summarize, the principle of conservation of momentum alone actually allows for an infinite number of possible outcomes, ranging from the perfectly elastic collision to the perfectly inelastic collision. Collisions between the steel balls in the Newton's pendulum happens to be highly elastic.
Can we do one ball on each side?
Sure, because the balls will be going in opposite directions, the total momentum before collision will be 0.
Will every ball come to rest after the collision?
No, these are elastic collisions. Besides momentum, kinetic energy must also be conserved.
Cool! But Papa, these balls did not go to school. Who taught them about elastic collisions and the principle of conservation of momentum?
There are three types of interaction: elastic, inelastic, perfectly inelastic. We'll elaborate more later on. At this moment, it is important to remember total momentum is always conserved for all this type of interaction. Now, let's begin with inelastic collision. In inelastic interaction or collision, total momentum is conserved, but total KE is not conserved. And total KE can be transformed to other forms of energy. It can be thermal, sound, or deformation energy, for example, spring that is being stretched. In a special case of inelastic collision, we have a perfectly or completely inelastic interaction or collision. Again, because it is a type of inelastic collision, total momentum is conserved, but total KE is not conserved. In addition, both bodies will stick together after collision. So we can say they have this common final velocity. If we write in equation form from conservation of momentum, since they have the same common final velocity, the equation can be simplified and written as follows. Let's look at work example 14. In this example, we have a bullet that is embedded into a ballistic pendulum, which will rise a vertical distance of 6 cm. We need to calculate the initial speed of the bullet. We let UB be the initial speed of the bullet and VC be the velocity of the combined body just after the impact. Let's use principle of conservation of momentum. But before that, we need to find the total momentum before the impact. The total momentum before the impact in the beginning will be just the momentum of the bullet because the pendulum is at rest. Before the pendulum rise, okay, just after the impact, when the bullet has been just embedded into the pendulum, the momentum is the mass of the bullet plus mass of the pendulum times the new velocity, combined velocity. Using principle of conservation of momentum, we equate both and we have one equation. Next, we use principle of conservation of energy to equate the gain in GPE at this point, GPE, and the KE just after impact. If we equate the two, we will be able to get the answer. Some of you may be thinking of using the KE at this point where the bullet is initially. Let's say the KE here is 10 joules and the GPE here, what do you think will it be? Will it be 10 joules? Remember, the bullet will actually penetrate the pendulum. Do you think there is energy loss here? Is it realistic to assume energy loss equals to 0? We cannot assume there's no energy loss, and this equation is definitely not true. Hence, we can only use the KE just after impact and compare it with the final GPE. And we have this equation. We will now look at perfectly elastic collision, or sometimes we just call it elastic collision. Like all interaction, the total momentum is conserved, and in this case, total KE before collision equals to total KE after collision. Note that during interaction, the total KE may not be conserved, as some KE may be converted to other forms of energy, and then reconvert back to KE after interaction. There are basically two ways to solve these elastic collision questions. Let's look at the first method, which is a long method. We call it method A. So we have a scenario of two masses moving to the right, and after collision, both of them move to the right as well. Let's apply principle of conservation of momentum since it is always true, and total KE is conserved because this is an elastic collision. KE is always conserved in an elastic collision. So the KE of mass 1 before collision plus KE of mass 2 before collision will be equal to the KE of mass 1 after collision and KE of mass 2 after collision. In a typical problem, we will just solve these two equations simultaneously to find two unknowns. So now you would know how to solve problems using principle of conservation of momentum. We will now look at work example 15. Two balls undergo elastic collision, meaning KE is conserved. You are told to calculate their speeds after the collision. We always start with principle of conservation of momentum. Sub in the values, you can form one equation. And since Ke is conserved, you can use a Ke equation. And from here, there are two unknowns and two equations, so you can solve. We will now look at the second method. For any elastic collision, we say that the relative speed of approach, how fast the object is moving towards each other, compared with the relative speed of separation, how fast the masses are moving away from each other after collision. Notice that in this equation, in the center, we have the same subscript. This is the way to remember. So U on the left, V on the right. And in the center, make sure you have the same number. It can be either 1 or 2, but these two must be the same number. So now we have two equations that we can solve any problems. As usual, we have our conservation of momentum, but now instead of using the K equation, we can use a relative speed equation. When you solve problems, do take note they are vectors, so make sure you consider their signs. With these two equations, you should be able to solve the equation. And this is the learning outcome. Now let's look at example 15 again. We will solve using method B. So what is the same is the principle of conservation momentum. From here, we get one equation. Instead of using conservation of kinetic energy, we will use this equation. The initial speed we have, so you can sub them in. Final speed we do not have. Okay, but however, this will help us to form equation 2. And now we can solve the equation simultaneously. Right, notice because there is no v square term, it is much easier to solve. To challenge yourself, you may use principle of conservation of momentum or conservation of Ke to derive this equation. Now, let's look at work example 16. In this example, we have head-on collision, which is elastic. I hope you remember what they mean. First, it is hard to visualize, so you draw a diagram to help you. Next, we determine the direction. So let's say the initial velocity of 2 kg mass is positive. For elastic collision, we use a relative speed equation and we use PCOM. So we have two equations, two unknown, you can solve them. Work example 17. This example is a special case which we want to show. So elastic collision between identical mass with one initially stationary. Okay, now we are supposed to determine the velocity of sphere V after the collision. So elastic collision, straight away we apply the relative speed formula and we use PCOM and you can solve the equation. If you look at it carefully, you will notice that sphere A and sphere B actually exchange a velocity. Initially, sphere A is moving with speed 6, but finally sphere B is moving with speed 6. Initially, sphere B is stationary, but finally, sphere A is stationary. So this is a special case where we have same mass and one of them is stationary. Let's look at another special case. In this special case, we have a light moving mass and a heavy stationary mass. In other words, one mass is much smaller than the other and the heavy mass is stationary. So assume the collision is elastic. Again, we make use of the two equations. Since it's elastic, we will use relative speed formula and then we use a PCOM. So we have two equations, two unknown, and you can solve. If you notice, the small mass rebound in opposite direction with almost the same speed. So the tennis ball initial speed is 2. Its final speed is also 2. So they are almost the same. And if you look at the final speed of B, it is very, very small. So it is similar to almost 0. And there is almost no transfer of Ke between M1 and M2. So this is the special case. In conclusion, these two cases represent the extreme cases of transfer of Ke in a head-on collision, and one of the object is initially at rest. The result can be generalized as follows. and it is very useful to solve A-level MCQ with this. So far, we have been looking at PCOM in one dimension, or collision in one dimension. We will now look at it in two dimensions. Again, the same condition applies. Where there is no net external force, PCOM will always apply, regardless whether it is one dimension or two dimension. In one dimension, they will occur along the same straight line, or this is what we call head-on collision. In two dimension, they are off-centered. How do we solve the problem? You just use vector addition method. A car of mass 1000 kg traveling at 15 meters per second is enter a slippery junction and collide into a bus. And the bus is moving in another direction. So you can see that they are not head-on collision because it is not the same straight line. The two vehicles remain locked together, meaning they will have the same final velocity after the collision. And you are supposed to find this final velocity. We will use the vector diagram to help us solve the question. You can see the car traveling due east and the bus due south in this direction. This is the initial momentum. The final momentum must be its resultant. So you draw the resultant. Since this is the resultant, you can use Pythagoras theorem to solve for VW and use tangent theta to determine the direction, and the direction is theta here, so it is actually south of east 63 degrees. In this case, we can use vector diagram quite easily because we have a right angle triangle. If it's not right angle triangle, the vector diagram may be difficult and you will have to use sine rule or cosine rule. And in cases where there are more than two objects in collision, vector diagram is going to be much more complicated. So let's look at another method, the component method. Component method, we will apply PCOM in X and Y direction. Let's call the X direction the east direction. So in the east, the initial momentum is just that of the car. The bus has no momentum in that direction, so it is 0. And final momentum will be the mass of both bus and car multiplied by its velocity in that direction. So we form one equation. Next, of course, we will apply PCOM in the y direction. In the y direction of the bus, the car has no initial momentum. So it will be just the momentum of the bus equals to the final momentum of the two vehicles. Solving them simultaneously, you are able to get the same answer. So now you have two methods using vector diagram and component methods. Using them, you should be able to apply the conservation of momentum to solve simple problems. In this case, this is an inelastic collision because Ke is not conserved and the body locked together. In fact, it is perfectly elastic. To summarize, in any interaction between two bodies, total momentum is always conserved. Total energy is always conserved as well. This is the conservation of energy. However, total Ke may not be conserved. This table summarizes it. For elastic collision, momentum conserved, Ke before collision is equal to Ke after collision. But during collision, it may not be conserved, as some Ke may be converted into other forms of energy during the collision. For inelastic collision and perfectly elastic collision, Ke is not conserved. Of course, momentum is conserved for all kinds of collision. However, something special about perfectly inelastic collision is that they travel with the same final velocity. Now we have completed the chapter on dynamics. I hope you find easy and start doing your tutorial. All the best.